Back in 2017, a paper from Kipf and Max Welling didn't just nudge AI forward, it completely changed the game for how AI understands connected data. This wasn't just another small step, it was a huge leap. It gave neural networks a brand new, powerful way to learn directly from the structure of things like social networks or citation graphs. So let's dive into what made this paper so incredibly groundbreaking.
To really get why this was such a big deal, you have to understand the problem they were trying to solve. So, imagine you've got this massive web of academic papers, literally millions of them. Your job is to classify every single one by subject. The catch, you've only had time to read and label a tiny, tiny handful. This is the classic challenge of semi-supervised learning. How do you use the connections between the papers to figure out the labels for all the rest?
Now, before this paper came along, researchers had a few tricks up their sleeve for this, but honestly, none of them are great. The field was kind of stuck between two main ways of thinking, and both had some pretty serious downsides. So on one side, you had methods like graph Laplacian regularization. The idea was pretty intuitive. Just assume that things that are connected are probably similar. And that's fine, I guess, but it's also really rigid. That assumption gets baked right into the math. Then on the other side, you had these graph embedding methods. These were way more flexible, but wow, were they clunky. We're talking these complicated multi-step pipelines that were a total headache to get right. You'd have to first learn the network structure, then take that result and feed it into a completely different classifier. It just wasn't clean.
So what was the big idea from Kipf and Welling? Well, they didn't try to build something even more complex. Their breakthrough was actually an act of radical simplification. They figured out a brilliant way to take the power of convolutional neural networks, the ones that are rock stars at understanding images, and apply them directly to the messy, irregular world of a graph. And you can see this philosophy right in the paper's own words. Now, I know this sounds super dense and academic, but the magic phrase here is first-order approximation. What that really means is they took an incredibly complex and computationally expensive idea, spectral graph convolutions, which needed to look at the entire graph all at once with some seriously heavy math, and they came up with a simple local version. Instead of needing a bird's-eye view of the whole network, each node just had to look at its immediate neighbors. It was this incredibly clever shortcut that it turns out worked just as well, if not better.
And out of that idea, the Graph Convolutional Network, or GCN, was born. And here's the key takeaway. A GCN doesn't just look at the features of a single data point in isolation, like the words in a document. It actively learns by baking the graph structure, all those connections, directly into the learning process itself, layer by layer. Okay, so how does it actually do that? Well, the engine behind it all is this beautifully simple and intuitive rule that gets applied at every layer of the network. Let's walk through it. You can pretty much think of it as a super efficient gossip algorithm. For any given node in your graph, it does three things. First, it gathers up all the features from its immediate neighbors. It's basically asking, hey everyone, what do you all know? Then it takes all that aggregated information and runs it through a standard neural network layer to process it. And finally, it uses that newly processed info to update its own features. So every node becomes a smart blend of what it was and what its local neighborhood is. That's it. Simple, right? But so powerful.
And this is where it gets really amazing. When you start stacking these simple layers, you let the gossip travel farther. See, with just one layer, a node only learns from its direct friends. But with two layers, the information from its friends of friends now gets passed along. By stacking more and more layers, the model can start to see and learn from these much larger, more complex patterns across the entire graph.
Now, all of this is a really nice, clean theory. But the big question is always, did it actually work? The answer to that was a massive, industry-shaking yes. Let's look at the results and see how this new model did against the heavyweights of the time. Okay, check out the key results here on these standard citation network datasets. If you look at the GCN, it didn't just squeak by the competition. It blew right past them, hitting over 81% accuracy on the Cora dataset. And here's the kicker. The paper showed it was also way, way faster to train than the other top methods, so it was better and faster. That's basically the dream in machine learning.
But numbers in a table can feel a bit abstract. They only tell you part of the story. The real magic, the aha moment that makes you really get it, comes from actually seeing what the network learns. Just look at this. On the left, that's the network at the very beginning of training. It's just a jumbled, chaotic mess, right? But now, look at the right. That's what it looks like after training with, and get this,
only a single labeled example from each of the two communities. Bam! The nodes have been pushed into these perfectly distinct clusters. When we say they're linearly separable, we mean you could literally take a ruler and draw a straight line to separate the two groups. It's incredible. The network figured out the entire social structure just by passing messages along the connections.
So yeah, this paper did way more than just introduce another state-of-the-art model. It really kicked off a revolution in how we do machine learning on graphs, and it created a legacy that, believe it or not, we all interact with pretty much every day. So why does all this matter to you? Well, the core ideas pioneered in this one paper are now the foundation for countless technologies you use. That recommendation engine suggesting what you should buy next, the artificial intelligence that's discovering new molecules for life-saving drugs, the systems that banks use to spot complex networks of financial fraud. Yep, they all have the DNA of this original GCN architecture in them.
The great power of the GCN is that it learns from local neighborhoods, but that strength also points to its biggest limitation and to the next great frontier in this field. It leaves us with this huge, fascinating question. How do we take these ideas and scale them up to learn from global patterns, from connections that might span billions of nodes all across the entire web? That's the challenge that researchers are tackling right now, and they're all standing on the shoulders of this one groundbreaking paper.
This is for entertainment purposes only.